Welcome in today's session. In today's class, we will cover the topic free radicals. In previous sessions, we have understood the carbocations, carbon ions, and we will continue to understand the topic free radicals today. To understand the free radicals, first we need to understand that what is homolytic and heterolytic fission. So once we have a covalent bond, as you can see here in this bromine molecule, this bromine molecule under different reaction conditions can break in two ways. One way can generate the anion and cation because the shared pair of electrons are broken in unequal distribution. Both the shared pair of electron goes with the one bromine atom and that get the negative charge, and one bromine atom is leave without any electron of the shared pair, it gets positive charge. But when it will be homolytic fission, like the shared pair of electron will share equally one electron with one atom, one electron with an atom. This generates a radical atom. An atom contains one unpaired electron, and that is known as free radical. So free radical is an atom or group possessing odd or unpaired electron. And because of this unpaired electron, this free radical is paramagnetic in nature, and this particular property of free radical help to characterize or to investigate that whether free radical is found in our reaction or not by various spectroscopic mechanisms to utilize the property of paramagnetism. So we will see how the free radicals are generated. Basically, to induce the homolytic fission in a covalent bond is not an easy process. It requires huge amount of energy. So to generate a free radical from molecule or to break a covalent bond under homolytic fission condition, we need energy, and this can be by both process, the physical process or chemical process. Physical process can be heat, like here in the very first example we can see that this is tetramethyl lead, and when it is heated it forms the methyl radical. So by applying the heat we can get the methyl free radical. And we also use certain reagents to generate a free radical in chemistry, and one of the most important reagent is benzoyl peroxide. As you can see here, this is benzoyl peroxide, peroxo linkage and benzoyl group. Benzoyl peroxide easily undergoes homolytic fission by this peroxo linkage to generate benzoyl peroxide radical. Another compound is the diazo compound, which used to generate the free radical. Here you can see at 300 degrees Celsius, this diazo compound can form the methyl free radical. Free radicals can also be generated by applying the ultraviolet radiation or radiation of higher energy, as you can see here in methane, and these radiations are useful to generate the free radical in the compounds having the carbonyl group. So this acetone molecule generates the methyl free radical. And one other way to generate the free radical is by electrolytic process, that by supplying the electricity in the system. And here you can see that this carboxylate anion under electrolytic condition, it changes into as carboxyl free radical. So we will see how the free radicals are stable with a different substitution. What is the effect of structure on the stability of these free radicals? See, free radicals basically contains one unpaired electron, and this electron wants to be paired. So it means this free radical is also have electron deficiency like carbocations. So the stability trend in free radicals are very similar with the stability trend in carbocations. As in carbocation free radicals, tertiary carbocations were more stable. In the similar way, in free radicals, tertiary free radicals are most stable. Secondary free radical are then, and primary free radical are then, and then methyl free radicals. So the stability trend is quite similar with the carbocations. Why? Because free radicals are also electron deficient compound. They have electron deficiency, and this electron deficiency is taken up by electron donating groups like alkyl groups. So tertiary free radical is most stable. This is one of the reasons, and the main reason behind the extra stability is the hyperconjugation, that is no bond resonance. Similar to the case of carbocations, hyperconjugated structures are also possible for free radicals, because in primary free radical it has 4, in secondary it has 7, in tertiary it has 10. So as the hyperconjugated structures are increasing, this increases the stability of free radicals. As in the case of carbocations, if there is a presence of certain groups which has a pi bond like allyl or phenyl substitution, the benzene, this increase the extra stability in the free radical. Why? Because the free radical electron can undergo with the resonance with this pi bond, and the case is very similar in case of benzyl radical. As you can see, this benzyl radical can go on the benzene here, here, and here. So due to delocalization of this free radical or free electron, this benzyl or phenyl group gives the extra stability to free radical. So if we have the substituted benzyl or pi bond in the molecule, this is even more stable than the tertiary free radical. The hybridization in the carbon free radicals are sp3 like the anions. So the structure should be tetrahedral, and one of the position of the tetrahedral site is occupied by one unpaired electron. As you can see here, for sp3 hybridization, one of the site is occupied by the free electron. So, in transition state, the carbon can be sp2 hybridized with planar geometry. So in transition state, when free radical is undergoing a certain reaction process, in the transition state it changes into sp2 hybridized carbon which have planar geometry. Then again in the product or in whatever the outcome of the process, the carbon again get the sp3 hybridization with tetrahedral geometry, and one of the site of tetrahedron is occupied by the free radicals. So now the detection of free radical, how we can detect the free radical, and as I told in very beginning, that the property of paramagnetism in the free radicals, because of presence of one unpaired electron, is very helpful in detection of the free radicals. So, and the technique by which the free radicals are detected is known as EPR, or electron paramagnetic resonance, or ESR, that is electron spin resonance. The particular electron of free radical which is free or not involved in bonding, that shows the signal under the electron paramagnetic resonance condition, and we can easily identify the signals with the peaks in the spectra. Now we will see what free radical can do in the reaction and how the free radicals are involved in the reaction. As you can see, once the free radicals are generated and See here, this by applying heat of peroxo linkage, the free radicals can be generated in homolytic fission manner. And I will show an example of radical chain mechanism, how this bromination of this allyl group is done under the homolytic fission condition with using the tertiary butyl peroxide. So the first step is the initiation. The chemical reagent which is used to generate the free radical, it breaks up and generate the free radical. Now the role of this free radical is to generate the free radical from the one of the reactants. Suppose we have used HBr as one of the reactant. So this generated free radical will extract one electron, and this will generate again a bromine free radical. Now this bromine free radical will react the pi electron and to generate the carbon free radical. As you can see, this is secondary free radical. And also the free radical can be generated on the primary position, but due to stability region the secondary will be generated, and predominantly reaction proceeds with the secondary free radical. And now this secondary free radical will again attach with the hydrogen free radical and will form a neutral molecule. In this way, the bromination of the reactant will occur, and the last step will be the bromine free radical undergo termination step, how it will react another bromine free radical to generate a bromine molecule. So this is the way how free radicals can involve or react under the chemical reaction condition. The three main steps of the chemistry of free radical, that first step is the initiation, the generation of free radical. Then the second step is propagation, how the free radical enter in the reaction to form the product. And the third step is termination, how the free radical form end up with a neutral molecule. So this is all the chemistry of free radical. So in today's session we learned what are free radicals, how they are generated, their stability, and their behavior of free radicals under different reaction conditions. So this is all for this lecture. Thank you very much.